Good afternoon, everyone. On behalf of all of us at the National Glass Association, thank you for making time in your busy day to join us for this month's installment of Thirsty Thursday. Before we begin, let's review a few housekeeping items. All participants will be muted for the duration of the conference to ensure minimal audio and video interruptions. We will hold a time for question and answer at the conclusion of Steve's presentation. You may use the Q&A feature in the toolbar at the bottom of your screen to submit your questions, which may be addressed verbally or with a written response. NGA's Glass Build Connect is just 2 weeks away. And the next slide, you'll see this is a 22-day event of content organized by daily themes and product showcases across all industry segments. September is for solutions. We hope to see you there, and visit glassbuild.com to learn more and register for free. Now I'm pleased to introduce today's speaker. Steve Thomas, PE, is Guardian's technical advisor for the Western US and Canada. He entered the glass industry in 2004, working for Advanced Structures Incorporated, ASI, which was later acquired by Enclose. In his role at ASI Enclose, Steve was involved in the structural design of landmark glazing projects across the country. He subsequently worked for SGH and Optimum Designs before joining Guardian in 2012. Steve is currently chairing the ASTM task group on the 5-year renewal of ASTM C1036 standard specification for flat glass, and is available to provide technical guidance on a wide range of glazing and glass considerations. Steve, I'll let you take it from here.
Thank you very much, Sarah. Thank you very much for that great introduction, and thank you very much, everyone, for joining us. It's great to be together, and I look forward to going through this presentation. So let me turn off the camera, and we'll dive right into it. So we're looking at preventing glazing surprises from the standpoint of appearance properties. And let me advance the presentation. There we go. So we just have some boilerplate disclaimers on the slide here, explaining that the content is for general information, and that the release of PDF copies is subject to Guardian's discretion. This presentation associates with learning credits, and correspondingly, we have certain specific outcomes. We want to determine how to properly view architectural glass. We want to identify how heat treatment can affect aesthetics. We want to evaluate cutting edge deletion relative to structural silicone glazing. And we want to evaluate the scope of prudent material compatibility verification. So let's jump into it. We have 3 sections to the presentation: appearance previews, non-uniformity mitigation, and perimeter planning. We'll begin with appearance previews. The most elementary aspect of appearance is to understand how to view glass. When we're looking at a hand sample of glass, we want to view it over a black background with the primary light source on the same side as the viewer. Again, when we're looking at a glass sample, we want to look at it over a black background with the light source on the same side as the viewer, because this correlates with the dominant light source, the sun, being on the same side as the viewer when we're looking at the glazing during daytime in the project application. We may also want to consider the glazing over a white background where there's significant light transfer from the side opposite the viewer. Again, with a white background, there's significant light transfer from the side opposite the viewer, and this correlates with the lighting from the side opposite the viewer due to electrification within the building as viewed at nighttime. We want to view glazing to the extent we can outside because we want to see it under a natural spectrum as opposed to the modified spectrum of artificial lighting. And of course, we want to see the glazing in a representative context. If we're looking at the glazing under a nice picturesque blue sky, that may be a very nice sky to look at, but it's going to shift the color of the glass in the blue direction. And we want to see the glass as it naturally appears on the building. So we want to look at the glass under a representative sky, typically a neutral sky. And if the sky is overcast, that means there's going to be diffusion of the lighting, and that light diffusion will assist our appearance observation of the glass. Of course, the sky changes over time. We want to account for that as well. And we also want to look at the glazing samples from a range of angles of observation. Now, progressing from glazing samples to full-size mock-ups, we want those mock-ups to encompass the full body of crucial conditions on the project. So if we have a serpentine facade like we see on the screen here, each of those transitions from flat to convex, convex to concave, and then concave back to flat again, each of those is unique to the others. So if we have a facade of this nature, we would want to represent all 3 of those crucial conditions. We want to evaluate uniformity, of course, and as you can see on the screen, the panel to the right has a slightly different color than the other two. We want to consider surface flatness. Of course, there's a lot of distortion here, and if we see something like this in terms of the mock-up, we would want to evaluate the flatness of the glass. And a little bit later in the presentation, we'll talk about how we can introduce a specification to address the glass flatness physically. We could also consider revisiting the glazing construction and deciding upon a composition with less outward reflectivity, so there's less visual prominence to the distortion. When we're looking at a full-size mock-up, we want to consider it over a range of backgrounds, specifically those that correlate with the actual construction. So if it's possible to build up in 3 dimensions behind the glazing, representing the occupancy conditions and considering various color tiles and lighting behind the glass as well as in front of it, that would be ideal. And again, we want to account for the range of sky conditions and view the glass from a range of angles of observation. Okay, so from hand samples to a full-size mock-up to the actual installation, we want to, again, maintain care. After installing a few glazing panels, we want to take a moment, step back, look at them, make sure there are no anomalies. We want to catch those as early as possible. If everything looks good, we can install a few more panels, inspect them. As confidence builds, we can space out these inspections, but nonetheless, it's important to continue inspecting the glass periodically. And of course, if any anomalies arise, we want to address those as soon as we can. Exterior glare mitigation. This is especially an issue in regard to concave facades. And an easy way to remember the term concave is that a concave curve is a curve that wraps around the viewer like a cave. So if you're looking at the glazing from the outside and it's wrapping around you, you have a concave facade. And as you can see on the screen here, if the sun is reflecting off of a concave facade, it can concentrate to a hot spot, both in terms of the energy from the visible range and from the infrared range. And so we want to navigate this by conducting astronomy studies, understanding the position of the sun within the sky across the service life of the application, and then understanding the specific implications of the hotspot in terms of glare, occupant comfort, and adjacent constructions, and implications on nearby transportation paths. Okay, let's move to non-uniformity mitigation, beginning with roll wave. And to talk about roll wave, we really need to introduce the heat treatment process. So in a nutshell, the way it works is we have glass that is to be heat treated. That glass is heated, and then the surfaces are cooled by forced air. And this causes the surfaces to remain in compression, which has the effect of strengthening the glass. Now, the issue in regard to roll wave is that as the glass is heated, it can deform between the rolls and then remain permanently deformed. As you can see written there, this is amplified for visibility, highly amplified. If we amplify it even further, we can see we clearly have a waveform. And so one way of navigating roll wave is to specify a peak to valley limit. The shorter the peak to valley limit, the flatter the glass. Now this does have its own constraint, and that is we could have multiple geometries with the same peak to valley dimension, the flatter ones being preferable to the more abrupt curves. And so a step further would be to specify the curvature of the glass. This is typically done in terms of addressing the lens power, but it may be more intuitive just to describe the radii of the glass. If we have large radii, that corresponds with flatter glass. So if we have a curvature limit that effectively says that over a lot of the glass area, most of the glass area, that the radii are of a certain diameter, a certain minimum the radii are of a certain minimum size, then the glass would meet the specification, otherwise the glass would not. And so if there's online equipment that can scan the glass surface and then run calculations to determine the consistency of the glass surface with that specification criteria, then an acceptance rejection decision can be made. So with a specification of this nature, whether a peak to valley limit or a curvature limit, there can be a binary decision whether or not to accept the glass. Bow is a situation that involves the glass edges. As you can see on the screen, it could involve the entirety of a glass edge or a localized portion. ASTM C1048, which addresses heat strengthened and fully tempered glass, introduces allowances for bow, but those bow allowances are fairly generous, so you may want to reduce them by a factor such as 2. Bistability is a situation where you could press on the center of a piece of glass, and the glass could suddenly move into a deflected state with a loud sound. And then if you press in the opposite direction, the same thing could happen in the reverse configuration. The situation is related to excessive perimeter heat during the heat treatment process, and it's a risk with square-like glazing. The aspect ratio is the long side divided by the short side. As we get to a square panel, the aspect ratio approaches 1. So glazing panels of that nature have an elevated risk. Low aspect ratios correlate with an elevated risk of biostability. One way of navigating the issue would be to ask that the project team reference recent projects demonstrating process control in regard to square-like panels. Iridescence is a situation where you could see spots or streaks in the glass, like we see on the screen here. All of this is highly amplified. This is viewed under conditions of polarized light, but you could see, smaller scale versions of this in glazing applications, whether the dots or streaks are white or different colors. Again, it's correlated with polarized light, and in terms of physics, it's attributable to the localized increase in the glass density where the quenching occurs. So the quenching blows cool air onto the glass, that slightly increases the glass density, inconsequentially really for any attribute, except for this phenomenon of the light transferring through the glass, possibly leading to these optics. Iridescence is not a cause for rejection, but if there are concerns about the issue, then a project team may want to reference some recent projects that illustrate the process controls. Moire is the situation where you could have multiple patterns overlapping with one another with slight mismatches leading to secondary effects. So if you move your head back from the screen and look at this pattern somewhat from a distance, you can see second order effects developing from the lower right toward the upper left. I'm sorry, from the lower left to the upper right. And then if we overlay a few more patterns, you can see that these secondary effects amplify. And so we want to avoid these effects because they can be very difficult to control. We want to avoid the consequences of simultaneous patterns by, of course, not using patterns on multiple surfaces, and then also not reflecting a pattern against itself. Even if the pattern is theoretically perfect in terms of its placement on two different surfaces of the glazing construction, if the lights have any distortion relative to one another, or if they have differential deflections, then Moire effects can develop. Spandrel glazing is glazing that's fully opacified, and it's used in building applications so that you have the appearance of glazing from the outside of the project, but you can't see to the inside, where these panels would be covering slab edges, mechanical equipment, or similar situations. So it's industry standard practice that spandrel glazing can provide a nice aesthetic to those outside the building. It's not designed to provide an acceptable aesthetic to those inside the building. So if you're looking at the spandrel glazing from the inside of the building, you could see pinholes or streaks. And again, this is not cause for rejection. The way that it should be addressed is with secondary opacification. So wall construction behind the spandrel glazing, so the occupants don't see these streaks or pinholes that are amplified by the intense sun shining through the glass. Condensation is a situation where a surface temperature extends below the dew point. In terms of the physics, the ambient temperature and the relative humidity together establish the dew point. And if either elevates or reduces relative to the other being fixed, then the dew point adjusts accordingly, upward with one, upward with whichever one is changing, and downward if it adjusts downward. Again, the surface temperature extending below the dew point leads to condensation. In the context of glazing, we're concerned about two particular situations. The first being the perimeter of an inboard pane of an IG assembly. So if we have an IG unit, we have two lights of glass typically, and we have a spacer and a frame. The spacer and the frame are the weak links in terms of insulating performance. There's conduction through the spacer and the frame that doesn't take place at the center of the glass. We have a warm side, a cool side. The two sides want to equalize. The energy wants to flow so that there's not a differential between the sides. And so coolness is extending inward. That coolness could reduce the surface temperature of the perimeter of the indoor pane, leading to condensation. And likewise, in terms of the heat escaping to the outside, there's less heat escaping to the outside at the middle of the panel relative to the perimeter. So at the perimeter, we may have effectively a heat trace, whereas in the middle of the panel, there's not heat transferring, so the exterior surface could remain below the dew point. In terms of the external environment, there's an enormous body of data available through websites like WeatherSpark or weatherbase.com. In terms of the interior of the application, if we could dehumidify, that would help to reduce the risk of condensation. And we also want to allow free air circulation. We're not proposing that heating and ventilation systems be directed toward the glass. That would help to control condensation, but it would also defeat the insulating performance. We're just proposing that there be freely flowing air to help properly mitigate the risks of condensation developing. In terms of quantification, the National Fenestration Rating Council offers a simulation-based condensation resistance metric, ranging from 1 to 100, the higher the better. And the American Architectural Manufacturers Association, now integrated into the Fenestration and Glazing Industry Alliance, offers a condensation resistance factor with a similar range from 0 to 100, although the NFRC and AAMA metrics don't precisely correlate with one another. Corrosion. In terms of overhead glazing, we want to slope the glazing so that corrosion doesn't develop. The situation is that if water collects in the overhead glazing, especially if it's at a minimal slope where the water would have to travel uphill, of course the water won't travel uphill, the water would then collect. The collection of the water would cause the glass to deform further, allowing for further collection, and you'd have this feedback loop of more and more water accumulating. And then as that water evaporates, the contaminants within the water would increase in concentration. In other words, if the level of contaminants stays the same, the amount of water reduces. And so as the evaporation process completes, there's a large level of concentration of contaminants, and that could corrode the glass. So if we have overhead glazing corroding, that's not an issue with the glass itself. That should be addressed in terms of the sloping of the glazing to prevent ponding in the first place. And likewise, at a microscopic level, if we have the potential for surface corrosion in terms of the crevices of a glazing product, we want to coordinate that to make sure that the texture is not introducing inappropriate risks. In terms of cleaning, we want to implement preventative measures. From a design standpoint, if we have metal trim pieces onto which rain could fall, forming a mist, and that mist then corroding the bottoms of nearby glazing panels, we want to avoid a situation of that nature. From the standpoint of construction, we want to protect the glazing from adjacent trades, and sometimes we would use a protective film in that process. When we're doing so, we want that film to be protective, of course, but we don't want it to be any thicker or darker than necessary, because the film could have the effect of amplifying the thermal load on the glass, and in a worst case scenario, breaking the glass. From a maintenance standpoint, we want to be sensitive to the cleaning agents used on adjacent elements of the building skin. Particularly in residential construction, brick wash can be detrimental to glazing systems, so we want to be sensitive to that possibility. In terms of the nature of cleaning, we want to be thorough without being excessively aggressive. We want to align the frequency with exposure. We don't want to risk scratching the glass by cleaning it too frequently, but we don't want to make the cleaning so infrequent that permanent corrosion could develop in the interim. We want to avoid cleaning in direct sunlight because we want to control the drying process. We want to use water or a mild cleaning agent, nothing acidic, alkaline, or petroleum-based. We want to use a soft brush or cloth. Depending upon the situation, we may eventually need to explore razor blades or steel wool. We certainly don't want to start in that direction, but depending upon the situation, we may very carefully eventually get there. We want to start with a soft brush or cloth, though. Once we clean the glass, we want to rinse away the cleaning agent and then dry the glass. And if we can't dry the glass, we wanted to monitor the dissolved solids content within the water to make sure that streaking doesn't develop. Okay, so let's move to perimeter planning. The first issue being the visibility of the low-E coating in contact with PIB in terms of structural silicone glazing applications. So we need to step back in terms of the supply chain to introduce this issue. So at the very beginning of the supply chain, we have sand, limestone, dolomite, soda ash, and so forth that are combined together to produce glass at high temperatures. Those mineral ingredients are mixed around 2,900 degrees Fahrenheit. They form a glass ribbon, a continuous glass ribbon. The manufacturer then cuts that ribbon into industrial stock sheets. What often happens is the manufacturer then deposits a low-E coating over the entirety of the stock sheet. The stock sheet is sold to a fabricator. They cut it to size. And then the fabricator would conduct edge deletion, meaning that they remove the coating from the perimeter of the final glazing panel. We see a blow up there, and that perimeter removal is known as edge deletion. And edge deletion is performed so we don't have a conductive path that could lead to glazing or lead to coating corrosion. And we also want to perform edge deletion to maintain the quality of the hermetic seal of the IG unit. Now, in regard to this aesthetic issue that we're getting to, let's change the color scheme for amplified visibility. We'll make the coating red, as you can see there, and the glass deep blue. And we'll take a look at the edge of an IG unit in profile. So we have the outside of the building to your left, the inside to your right, the coating on the number 2 surface. We have primary seals P and a secondary seal S. And those letters also correlate with the common sealants that are used, probably the isobutylene, PIB, and silicone as the secondary seal. Now, if we have a structural silicone glazing application or a structural glazing tape application, In those situations, we don't have metal trim pieces on the outside of the construction. We have only the framing behind the glass. So if you're looking at the glass from the outside, as we see here, you're able to see the termination of the coating above the primary sealant. And the issue is that the color of the coating in the vision area and the color in front of the primary seal could be appreciably different from one another. So we don't want this to be a surprise to the project team. We want this to be evaluated at an early design stage, typically in terms of full-size mock-ups. Another consideration with regard to perimeter planning is material compatibility. And in a nutshell, I realize this is much easier said than done, but we're looking for compatibility verification from the standpoint of all materials in the complete context of the application, attained through proactive coordination. So let's elaborate. In terms of all materials, we're talking about all materials within or near glazing systems, including those that are not in direct contact with one another. So if we have an off-gassing of one material, it's possible for that off-gassing to result in an engagement with a material that's not immediately in contact with the one that's off-gassing. In terms of the complete context of the application, we're talking about full aesthetic and functional compatibility over all of the load cases, all of the load case combinations, all of the service conditions, everything combined together over the full intended service life of the glazing system. And then in terms of proactive coordination, we want to maintain supplier relationships so that even if there are unpublished chemical reformulations, we want those integrated into the project team's considerations. And we want to aim for appropriate testing to fully validate all requirements. So in terms of summarizing what we talked about, we went through appearance previews. We discussed hand samples, full-size mock-ups, and then the project installation. In terms of non-uniformity, we looked at roll wave, iridescence, and condensation. And then in terms of the perimeter, we discussed low-E coating edge deletion relative to structural silicone glazing applications, and the importance of complete material compatibility verification. So I hope that was helpful, and I'd be happy to address any questions.
Great, thank you, Steve.
Sure.
We have a couple that have come in. First one,
Great.
How does ASTM address flatness requirements for insulating glass units?
Well, in terms of the nature of the glass itself, or the glass rather than the overall unit, there's not an ASTM limit in terms of what the roll wave metric should be. That's a project team decision based upon the relative priorities of the application, considering cost and the nature of the glazing construction. If it's highly reflective, a more restrictive limit would be desirable, because as we eventually approach mirrors in terms of reflectivity, any amount of surface distortion becomes highly amplified. But in a nutshell, there's not an ASTM limit in terms of the flatness of the glass. There may be some provisions available through the Insulating Glass Manufacturers Alliance, also integrated now into the Fenestration and Glazing Industry Alliance, but that would be a good resource for nuances of IG construction.
Okay, great. Next question, during construction, what kind of film protection do you recommend?
Well, there isn't a particular film, but conceptually, we want to, of course, protect the glazing from adjacent trades. And the issue is that if we have a film that's dark in color especially, but also if it's thicker than needed, it effectively causes the glass to become tinted. And of course, tinted glass should often be heat treated for thermal stress management in the absence of advanced analyses. There's also the dynamic that if the film is applied to the glass, it's restricting the heat transfer away from the glass in terms of the reduced circulation. So it's thermal stress management is a complicated subject to address. You know, conceptually, if we can stick with a clear film, that would be ideal. If the film needs to be either darker or thicker, we would aim for thickness over darkness. And then if we need to migrate toward darkness, we would go there. But we want to be sensitive to the thermal stress implications in that process.
Okay, thank you. Another question. Why, after edge deletion, is some of the coating below the spacer?
The coating is present there so that we don't have the possibility of the coating not covering the full vision area. So there's, of course, a tolerance with every operation. If we ideally said that we wanted the coating to end right at the start of the PIB, like I said, there's a tolerance involved in everything, and so it's feasible that the coating may stop short or the coating may extend further. Now, if the coating extends further in most applications, that's fine because it's hidden by the framing system. But if it's not covering the full vision area, then that could be a big issue. So in a nutshell, to accommodate tolerances, we want the coating to extend farther into the PIB area. And again, it's not an issue in any application where the edge is captured, but where the edge is visible, it's sort of an inherent aspect of the situation.
Okay, excellent. Well, at this time, that takes care of the questions that have been submitted via the chat. And Steve, we thank you very much for your time and preparation for today. And as I'm saying, a couple more have come in, if you don't mind, since we have a few more minutes. But I did want to reiterate to everyone on the meeting that this is being recorded. So this will be available on glass.org for later viewing as well. Next question, you refer to compatibility between the PIB and other glazing materials. Is this issue the effect of glazing materials on the IGU edges seals?
Well, there can be all sorts of compatibility complications. In terms of general categories, there can be appearance issues where there's still, say, the bond functionality, but there could be, say, yellowing or a color change of some sort over time. And then in terms of functionality, the more crucial situations are where the quality of a chemical bond could be reduced. So it's a complicated issue because every situation is different, and it ultimately depends upon the nuanced chemistry of every single material involved in the project. And when we're talking about components that have various materials that comprise the component, it just becomes that much more complicated. So there's not a specific issue in terms of two particular materials. In a localized area, there are particular materials that have that are of greater concern than others. But generally speaking, we want to make sure that all the materials are compatible, and we want to do that as methodically as possible.
Okay, and in a similar vein, who should verify that material compatibility?
That's a good question. Ultimately, it would be the project team's responsibility. In terms of a practical approach to that, it could involve reaching out to the manufacturers and asking about test data. But the most methodical approach, the ideal approach, is that all of the materials would be tested specifically to that project, which would encompass the possibility of chemical reformulations in the interim, since testing within other contexts.
Okay, thank you. Another question, is using a non-tempered laminated glass better than an equally thick tempered piece of glass used in shower glass or building facades?
Okay, so if I understand the question, just correct me if I have this wrong, Sarah. We're talking about the thickness of the tempered glass relative to a laminated construction. So we have either tempered or laminated, and the question is in regard to the strength of those two relative to each other? And
relative to a roll wave, yes.
Okay, so yeah, if we have laminated glass and the laminated glass is comprised of annealed lights, then that would likely be flatter than the tempered glass. So if we're aiming for flatness, that would be a way to go. Now, when we're laminating glass, and especially when we're laminating heat-treated glass, each of those lights has its heat treatment distortion, and there's no way to guarantee that two lights have the same heat treatment distortion pattern. So when we laminate two heat-treated lights together, we're going to have the effect of amplifying the distortion. Now, it's true that in some cases, the peaks and the valleys will align and they'll cancel each other out, but what you'll visually see are the locations where they're additive. So if we're concerned about flatness and there are no other risks involved in proceeding in this path, we could pursue annealed laminated glass. From a structural standpoint, I would expect in most cases that would offer less strength than a fully tempered approach, because when we have a laminate, there can be some movement along the interlayer that effectively reduces the structural capacity of the glass. And if we're using annealed glass versus fully tempered glass, there's of course a differential in the structural capacity there.
Okay, thank you. We have 4 more questions, and then we will need to wrap this up. Okay. Next question, is there a perceivable color shift for low E coatings on clear versus low iron glass for the same coatings?
There should be no observable color shift within the framework of ordinary architectural expectations. So in other words, if a product is produced according to its specifications, it should be consistent with typical architectural requirements. So there should not be an appreciable color variance that's observed regardless of what the substrate is. Nonetheless, though, low iron has less color in it, and so it tends to be less forgiving than other types of glass relative to the issue. But in a nutshell, there should not be any objectionable issue in regard to color shift, regardless of the substrate.
Okay, great. Next one, at what point do elevation changes create distortion in an IGU? Are there ways to mitigate that other than breather tubes that don't put the argon gas at risk of leaking out?
Yeah, that's a very good question. I've seen numbers in the neighborhood of 2,000 to 2,500 feet in elevation difference, at which we want to consider capillary tubes or breather tubes. And yeah, that's a fairly common question. What do you do about argon in those situations? If the elevation difference is within the range where we can address the issue using refrigerated trucks, so in other words, addressing the thermodynamics in terms of temperature rather than pressure, that's one way to retain the argon. But if that reaches its limit, then the situation can become more complicated. There's some nuanced ways to potentially address that, but the first step would be to consider refrigerated trucks.
Okay. Also, in the same vein with IGUs, do you recommend a WEEP system be in place to ensure adequate airflow between the IGU? Does it allow water and moisture to escape from behind the glass?
Well, in terms of the IG unit itself, we want this unit to be hermetically sealed. So we don't want anything entering or exiting the IG unit. We want it to be hermetically sealed across its full service life. If there's any moisture migration into the unit, then that could result in fogging, which would be objectionable and would constitute a failed unit. So we want that seal to be as permanent as possible. Now, in terms of spandrel glazing and shadow boxes, there can be various detailing approaches as to what to do with the space behind the glazing. But as far as the IG unit itself, it should be hermetically sealed.
Okay. Why are there a lot of glazing specifications coming out calling for heat soak requirement?
Well, heat soaking is a way to address the possibility of a nickel sulfide breakage. So the situation is, if there is a microscopic inclusion of nickel sulfide within glass, and the glass is fully tempered, there's the possibility, in rare situations, that the glass after tempering could spontaneously break when that inclusion changes state. And so the heat soak process is a way to address the issue. If the glass is heat soaked, the heat soak process involves heating the glass and then cooling it again. And it generally has the effect of causing many of these inclusions, if they exist, to break during that process rather than to break later. So if there's concern about the presence of inclusions in tempered glass, this is an avenue that could address it. Its applicability varies based upon the situation. If it needs for structural purposes, then it could be very costly to replace the glazing panel, and it may make a lot of sense to heat soak the glass relative to that situation. But if we're talking about a small ground level window where it can be easily replaced, then heat soaking may not be the right approach.
Okay, great. And, one final question regarding iridescence. Can you comment on what is acceptable and is there a standard tolerance?
Well, according to ASTM C1048, iridescence is not cause for rejection, so it's considered to be an inherent aspect of glazing. Now, what we showed on the screen, remember that was a highly amplified version of the situation because we were looking at it through polarized lenses. Iridescence correlates with polarized light. Light can polarize naturally when it reflects off of a large body of water or a flat continuous surface. And when we're wearing polarized sunglasses or using polarized lenses like those as were used in the image we were looking at, then the situation becomes highly amplified. But in a nutshell, iridescence is not cause for rejection. If there are concerns about iridescence, a good practice would be to look at some past projects from the project team and assess the ability to provide glazing that's in line with expectations.
Okay, excellent. Thanks very much, Steve, and thank you to all of our participants for your excellent questions. That will wrap up our webinar for today, and we hope to see you in just a couple of weeks at our Glass Build Connect event. It's 22 days of programming and 5 daily content themes. Expect on September 17th, as you'll see on our next slide, we are having our version of Thirsty Thursday incorporated into Glass Build Connect. Should be a fun session on the glass evidence for a second shooter in Dallas. In addition, at the end of the month, we'll be holding an AIA accredited session in collaboration with Architectural Record. There's a glass for that, highlighting all of the unique and highly innovative ways that glass is being used in architectural design. So the entire month will be worth adding to your calendar, and these are just a couple pieces to put on your radar. So we hope to see you again soon, and thanks very much for your attendance today. Thank you, Steve.
Sure. Thank you, Sarah. Thanks very much, everyone.